All right. So there was the question about the homework, and it was, you said it was number 46.
Yep.
Yeah.
Okay, let me share my screen because I've got that up here. Do you remember which section it is?
2.1.
2.1, okay.
This is 46, right?
Mm-hmm. Yeah.
Oh, close, close, close. All right, so that look about right? So we've got, assume that all functions are defined on the interval AB. If y1 and y2 are solutions of these two independently, show that the linear combination of them is a solution to this other differential equation. And then the second part is to show that if both are solutions to the non-homogeneous, then their difference is the solution to the homogeneous. And then, let's see, then use the first part to show that if y1 is a solution of a non-homogeneous and y2 is a solution of a homogeneous, then y1 plus y2 is a solution of the non-homogeneous. Okay, so basically what we're doing here is we're proving what we've been using, kind of. But basically what this is going to say is that you can take any solution to the homogeneous and add it to any other solution and still be a solution to the original differential equation. So let me just write a couple of things down up here so then I can jump to the whiteboard. All right, so I'm going to stop sharing. And then we're going to go to the board. All right, so I just wrote down the kind of the most important bits of this, but we've got the two differential equations with their solutions y1 and y2. And we want to show that the C1y1 plus C2y2 is a solution to this second differential equation. All right, so here's how I would do it, just with a good old plug and check. We're going to go with y is equal to C1y1 plus C2y2. So y prime is going to be C1y1 prime plus C2y2 prime. So let's put that into this differential equation. So we're going to get C1y1 prime plus C2y2 prime plus p of x times this original function, C1y1 plus C2y2. So this last line I just wrote is the left-hand side of this differential equation. Excuse me. So I'm doing the usual, just starting with one side and seeing if we can make it look like the other side. All right, so what I'm going to do, I'm going to distribute, but I'm going to group everything with C1s together and everything with C2s together on the other, in another group. So we'll get C1 times y1 prime plus C1 times p of x times y1. So that's those two pieces. And then similarly, we're going to get a C2 y2 prime plus C2 p of x y2. I just rewrote them. But now let me factor out those c's. So I'll give you a chance to kind of catch up here. But are we good with the algebra? Yeah. All right. So now what we're going to do is I want you to look at what's in those parentheses. We've got y1 prime plus p of x times y1. And if you go back and look at what we know about y1, right, at the very top here, y1 is a solution to this differential equation, which means y1 prime plus p of x times y1, I know that equals f1, because that's what it means for it to be a solution. So this piece right here, if I kind of run it back up, it's going to be C1 times F1 of X. Because all of that is equal to F1 by the definition of what Y1 is. Right? Do the exact same thing with the other one. Now we've got a Y2 prime plus P of X times Y2. And we know that that satisfies the second differential equation. So we're going to get C2 times F2 of X, which is exactly what we were trying to show. So basically what this just said is that if you have two differential equations and you form a linear combination of it, then the individual solutions, if you take a linear combination of them, the same linear combination of them, it'll be a solution to that as well. All right, so before we go to the second part, how do we feel about that first part? We good? Say, Mike, are you actually outside, or is that just a background screen?
I'm actually at the base of Powder Bowl.
Nice.
Yeah, I'm up here with the homies. We're chilling out at Groove Park for the day, but I figured I'd jump in this for a little bit.
So I actually then, I feel really good about this. Did you choose me over being out there?
Yeah, I can hang out with them later.
All right, so we good for the first part? So now let's look at the second part. So the second part, I'm gonna erase some of this stuff. So the second part, we want to do kind of the same thing, where we're taking a linear combination, but this time we just have one differential equation. Do you guys remember what it was equal to? Was it like G or H or F, or it doesn't really matter?
I believe it's g of x.
Okay, let's call it G. All right, and we've got that y1 and y2 are both solutions to this. We want to show that y1 minus y2 is a solution to the homogeneous. So let's just look at what happens when we go with y equals y1 minus y2. So y prime is going to equal y1 prime minus y2 prime. Let's put this stuff into the differential equation. So we get y1 prime minus y2 prime plus p of x times y1 minus y2. And let's just see what we get. We want to show that we get 0, right? We want to show that it's a solution to the homogeneous. So again, let's distribute, but let's group according to the y1s and the y2s. So if you look at this first part, I'll put parentheses around them. What we know about this is that it's going to equal g of x, because y1 is something that makes this differential equation true. So that turns that into g of x. The other one, if I factor out a minus sign, you notice we get a y2 prime plus p of x times y2. Well, that also equals g of x because y2 was the solution to the differential equation. So we get g of x minus g of x, which of course equals 0. So we do know then that y1 and y2, if they are both solutions to a non-homogeneous, their difference will be a solution to the homogeneous. All right, so there was part B. We okay with that one? I think that one's a little bit easier to show. But now let's go to part C, and kind of the important part, which says that, let me look, I'm going to make sure that I'm using the right letters and things. I'm not going to share the screen. I'm just going to pull it up. So it says, show that if y1 is a solution to this guy, so y1 is the solution to the original differential equation, and y2 is a solution to the homogeneous. We want to show y equals y1 plus y2 solves the original, solves the non-homogeneous. All right, well, let's do it like we did before. Let's just plug it in and hopefully we end up with g of x. So obviously y prime then is going to be y1 prime plus y2 prime. So if we put this stuff in, let's distribute and group. So we get y1 prime plus p of x y1 plus y2 prime plus p of x times y2. So the first set, that's going to equal g of x because y1 was a solution to the first differential equation. This second pair, that's going to equal 0 because y2 was the solution to the homogeneous. And of course, since g of x plus 0 equals g of x, we see that this guy, y1 plus y2, also satisfies the original differential equation. So the moral of this, the whole point of all of this, is that if you have a solution to the homogeneous, you can add that to a solution to the non-homogeneous and get another solution. So it's basically a way that we can build solutions. We just add solutions to the homogeneous as much as we want. And we can add linear combinations of them, like we saw from the first part. All right, so was that better for whichever number this was, number 46? Yeah. Any
Definitely.
other homework questions we want to look at?
Can we look at 47?
47?
Yeah.
All right.
Some nonlinear equation can be transformed into linear equations by changing the dependent variable.
Okay, I'm going to go ahead and share my screen again, and we'll take a look at it. Okay, so it says some nonlinear equations can be transformed into linear equations by changing the dependent variable. All right, so basically this is, if you've got something that's not linear, sometimes you can fake it and make it so that it is, so that you can use linear techniques. But it says show that if g prime of y times y prime plus p of x is g of y equals f of x, where y is a function of x and g is a function of y, then the new dependent variable z equals g of y satisfies the linear equation given. All right, so let's go ahead and let me write down all this important information again on the board, and then I'll switch back. So we've got g prime of y times y prime plus p of x times g of y equals f of x. So that's our if. Then we want to show that z equals g of y satisfies z prime plus p of xz equals f of x. Okay, so we got all our information. Let's go to the board.
All right, so you can see where this whole going to linear comes from, right? Because now in Z, this is a linear. The original one is not in general because G prime may or may not be 1. Like if it's some function of Y, this is clearly nonlinear. So let's show that this actually works. So basically, I just want to take Z equals G of Y and put it into this differential equation. So what we need then is Z prime. So what's the derivative of G of Y going to be?
G prime of y.
Okay, so we get G prime of Y. But there's one more piece to this. We need to have a Y prime. Why? What did we just do there?
Chain rule.
Yeah, that's good old chain rule, right? We differentiate the outer function and we multiply by the derivative of what's inside. And we need to do this because remember the original independent variable is x. So all of the original things are derivatives in terms of x. So since we've got a function in terms of y, this actually needs to be chain rule. So now let's put it into the differential equation. So we get g prime of y times y prime plus p of x times g of y. So that was this right here. And notice that that's exactly what we started with our if. So we know that this thing actually equals f of x. So this was z prime plus p of x z equals f of x. And we're done with our proof. So the whole point of this one is just to tell you that if you've got this form, if whatever this is, this nonlinear deal, is such that this function of y has its derivative as the multiplier on y prime, you can do a substitution and turn it into linear first order. So this then we could solve for z. And once we've got z, we know that equals g of y and yada, yada, yada. All right, so is that better for that one, JP?
Yeah, I just missed the whole chain rule thing.
Okay. All right, cool. Anything else from homework? All right, well, hearing none, we're going to go ahead and move on. All right, so last time we basically looked at separable, right? We were looking at separable differential equations, figured out if we could separate them, we just had to integrate both sides. and looked at the difference between like implicit versus explicit solution.
So today what we're going to do is we're going to start by talking about existence and uniqueness. We're going to talk about when do we know we have a solution, what are the requirements that guarantee that we're going to get a solution, and then if we're guaranteed a solution, what extra conditions will make it so that we're guaranteed a unique solution. And you've seen with initial value problems that we've been able to find multiple solutions sometimes. Like great example, there was the one where, well, Will's favorite, y=0, right? That often is a solution, but not necessarily the only one. So we've seen that you can get more than one, but we really need to figure out when is it that we get more than one versus when are we guaranteed just one. So we're going to look at existence and uniqueness, and then we're going to turn our attention to other differential equations that while they're not separable, can be turned into separable because of their form. And this is, again, kind of what I was hinting at before when I talked about how with differential equations, it's all about pattern recognition. That's a lot of what we're going to be doing, is being able to look at an equation and go, oh, that one's not separable, but it's one that we've seen before. And so, you know, like there's a group we're going to look at called the Bernoulli Equations. This class is such that they always take the same form and are separable. So that's going to be our goal today. But let's start with existence and uniqueness. How do we know that we've got something? And then once we've got one, how do we know that it's the only one? All right, so I'm going to go to the whiteboard again. And let me just start with the existence theorem. So the existence theorem is exactly what it sounds like. It's going to tell you when you know you've got a solution. So it goes kind of like this. If f of xy is continuous on an open rectangle, and we'll talk about what this stuff means. Okay, so on an open rectangle that contains x naught, y naught, then the initial value problem, y prime equals f of xy, comma, y of x naught equals y naught, has at least one solution on an interval AB that contains x naught. All right. So let's talk about this and let's see if we can make sense of it. So f of xy, that's not the solution to the differential equation. What I want you to notice about f of xy is that's what y prime equals. So if you have a differential equation and you solve it for y prime equals all that other crap, that's this f of xy. Okay, so that's not the solution to the differential equation. It's basically just, it is the differential equation. It's what y prime equals. All right, so that's first things first. Obviously the x naught, y naught, this point, this is our initial value. So this is the point that we get from
whatever our given information is. And then we say we need this to be continuous on an open rectangle that contains x naught, y naught. So let me just go ahead and put some coordinates here. So there's our x naught, y naught. So the solution to the differential equation is going to go through that point because it's the initial value problem. All right, so we need an open rectangle. Well, you remember open intervals are all the, we're going from somewhere to somewhere with the parentheses. Well, an open rectangle is kind of similar, except it's got 2 dimensions too. So this would be an open rectangle that contains the point x naught, y naught. We don't worry about the boundary. The boundary, if that was included, would be a closed rectangle, but this one's an open rectangle. All right, so let's look at what this statement says again. We need f of x, y, whatever this y prime stuff is equal to. It has to be continuous on an open rectangle that contains this point. So if we can find a rectangle, we can find one rectangle, open rectangle, where this function is continuous, then we're guaranteed to have at least one solution. So there could be more than one, because this just says at least one. And that's why this is called the existence theorem. So really what we're going to do is, given some sort of a differential equation, we're going to look and see, can we create an open rectangle about this point, about the initial value point? And if we can create one where this function is continuous, then we know for sure we have at least one solution. If it's not possible, then it's not possible. All right, so let me just show you a couple of examples. We'll talk about, obviously I'll show you one where we are guaranteed existence, and I'll show you another one where we're not. So let's start with this guy. Let's say we've got y prime equals the square root of x squared plus y squared. So this is not a linear differential equation. You see that from the y squared. Even worse, there's a square root involved too. But that guy is not linear. However, it is first order. All right, so again, the question is, are we guaranteed a solution to this if it's an initial value problem? So let me give you an initial value. Let's say that what we've got is y of 0 equals 1. So I'm going to start by drawing this point, 0, 1. So 0, 1 is over here. And so the question is, can I build a rectangle around that so that all of the x's and y's that are in that rectangle make it so that f of xy is continuous? So f of xy in the context of this problem is the square root of x squared plus y squared, right? It's the thing that y prime equals. So far so good? So let's look at this guy. F of xy equals the square root of x squared plus y squared. Are there any places where that function is not continuous? So this one's perfectly fine. Square root of x squared plus y squared. Because think about continuity issues. We have to worry about domain issues. Turns out that there are no domain issues with this. Even though it's a square root, since we've got a sum of squares, we don't have to worry about a negative being in there. Okay, so that thing is going to be, that thing's got a perfectly fine domain. And you may remember that square roots are continuous on their domain. So can I build a rectangle around this such that everything is good? Oh yeah, there you go. There is an open rectangle where if you take any of the points in that rectangle, this function is continuous. So I know that there will be a solution. Do I know that it's going to be unique, that there's only one solution? No, I don't know that yet, but maybe we'll find out. All right, so this one guarantees a solution. And in fact, it doesn't matter what our initial value was. Like I chose y of 0 equals 1. Since there are no problem spots with this in terms of continuity, it's going to be good always. All right. So, okay, questions? Well then, let's see, is our point 0, 1 or 1, 0? Yeah, it's 0, 1. Sorry about that, Monty. All right, so I get technically the picture should look like this. Luckily, nothing changed. Right, but yeah, nice catch. All right, so there's an example of where we know we're guaranteed. Right, we're guaranteed a solution. So let's change this just a little bit. And let's look at something like this guy. Let's say we've got y times y prime plus x natural log of y equals x squared. So same question about this thing and an initial value. Let me actually, real quick, I apologize. I'm going to make this a y plus 1 inside of the natural log. But let me give you an initial value problem. Let's say that we want to have the initial value of y of 0 equals 0. So the question is, are we guaranteed a solution here?
In the natural log, is that y plus 1 or?
Y plus 1.
Okay.
Okay.
I wanted to make it so that it was defined if I plugged in 0. That's why I shifted it over. All right, well, on the graph, we know where 0, 0 is. No big deal. But let's figure out what f of xy is. So we have to start by solving this for y prime. So we're going to get y prime equals x squared minus x natural log of y plus 1. And then we divide by y. So there's our y prime equals. And so this is our f of xy. So where are continuity problems with that?
When y is equal to 0.
Okay, when y is equal to 0, we definitely have a problem. We also have a problem if the y's are less than
-1.
-1,
Yeah.
right? -1 or less, we're going to have a problem. Any issues with the x?
Not really from my can so.
Yeah, in terms of the x's, there are no issues. So really the only issue is going to be y is 0 or y is less than -1. All right, well, let's look at our initial value. Our initial value says we want y of 0 equals 0. So what we need to see is, can we form a rectangle around that such that our function is going to be fine and be continuous in the entirety of that rectangle? And this one you guys should feel pretty good about. No, we're not going to be able to build a rectangle around this, because any rectangle that contains this point is going to have places where y is equal to 0, because that point itself has a y that's equal to 0. So what does the existence theorem tell us about this one? So I see you guys shaking your heads.
It doesn't, because for it to tell us anything, then it would have to apply to that condition, right?
Okay, so what this tells us is exactly what Monty just put into the chat, where we're not guaranteed a solution. Is there a solution to this differential equation? Maybe, maybe not. Okay, the existence theorem just tells you if it's guaranteed to exist. If it fails, meaning this situation where we can't build the rectangle about the point, it actually tells us nothing. And in fact, there is a solution to this differential equation, this initial value problem. In fact, it's specifically y equals 0. Take the function that's identically 0, because we're going to get 0 times y prime, which is also 0. Oh, I lied. No, I'm good. We're good. You get 0 times 0. And then when we put 0 in here, we get natural log of 1, which is also 0 times 0, and equals 0 times 0. So it is possible to have a solution even though the existence theorem tells you that it failed. Right? So this just tells you you're not guaranteed. You may or may not. We could change the initial value though. Like if the initial value was, let's actually just make it y of 0 equals 1. So now our point is up here. This now we'd be guaranteed a solution, because we can create a rectangle about it that would not contain any of the problem spots. So it's all about where we start. It all depends on the initial value in terms of existence or not. So it's not the differential equation itself. It's the entirety of the initial value problem. All right, so how do we feel about what we need to look for in terms of existence? Okay. Thanks for the feedback, appreciate it. So let's move on then to uniqueness. And I'm not going to prove this one, by the way. The proofs of these are really, really gnarly. So we're just going to accept them as fact. All right, so there's existence. So then what about uniqueness? So uniqueness is going to tell us exactly that. It's going to tell us if we have a solution, then what has to be true for us to be guaranteed just one solution. All right, so here's how this is going to start. First, that same f of xy it needs to be continuous, but also the partial with respect to y is also continuous. And then we go to the, on an open rectangle containing x naught, y naught. So notice we just bumped up the conditions. We already saw that for existence, we needed f of xy to be continuous. But now we also need the partial with respect to y to be continuous. So if we have both of those, then what we know is that if we've got the initial value problem, y of x naught equals y naught, it has a unique solution. On an open interval containing x naught. So now we just jumped from having a solution to having one and only one solution. So it's really the same kind of idea. We're still trying to build this rectangle. We just need to make it so that both f and f sub y are continuous in. So let's look at an example. And in fact, we'll take one that we were guaranteed a solution to just a minute ago. One that was y prime equals square root of x squared plus y squared. But this time we're going to look and see, is that going to be a unique solution? What does this tell us about that? All right, so I'm going to go ahead and erase this and go back and put that function up again. Okay, so we saw this one before, and we saw that f of x, y here, it was good everywhere. There were no issues with continuity. Everything was fine. But now, let's look at f sub y. So we know we are guaranteed a solution, but the question is it unique? Well, the derivative of this with respect to y is going to be 1/2 x squared plus y squared to the minus 1/2 times 2y, which is y over the square root of x squared plus y squared. Now, this one, you can see there are definitely issues to. Right? What's a problem?
Where both x and y are equal to 0.
Right. So if x and y are both equal to 0, there's a discontinuity. Other than that, though, everything is fine. So notice what happens with this is it all depends upon the initial value. Right? We're looking at y of x naught equals y naught. So here's kind of how this is going to break down. We have two cases. The one is where they both equal 0. So this is going to be y of 0 equals 0. This one is we know nothing. So I'm going to put unique, and I'm going to put a question mark because we don't know. Could it be that there's a unique solution that passes through that? Maybe, but this doesn't tell us. However, if one of these is not 0, then we are guaranteed unique, and I'm going to make that an exclamation because we do know that it's going to be unique. And hopefully you see that, because as long as one of those is not 0, we're going to be able to step away from the origin even by the slightest little margin, and that will allow us to build an open rectangle. So the other thing that's kind of important about this is the size of the rectangle, like how close we can get. And what that really tells you is the largest interval over which you're guaranteed to have these solutions. So let me give you a specific one here. Let's say that we've got same differential equation, but for this initial value problem, let's go with y of 0 equals 1. So we've got a specific one now. So we are now guaranteed a unique solution because we're no longer at 0, 0. Well, let's look at the graph. So 0, 0 was the problem spot, but right now we're up here at 0, 1. So thinking about a rectangle that needs to be open, the real issue is I can't hit the origin. So there's going to be like a lowest point I can reach, right? I can go down a bit, but I have to be kind of careful. In terms of going up, I can go up as far as I want. How about left and right? How far can I go? Pretty much as far as I want, right? So this one, we are guaranteed a solution. We're guaranteed a unique solution. So I'm going to write here, unique solution guaranteed. And I'm going to put on minus infinity to infinity. So I'm going to be able to go as far as I want either way and have a unique solution. So let me change it. Instead of y of 0 equals 1, let's make it y of 1 equals 0. So now if I draw that graph, we're going to go through the point 1, 0. So I can still create a rectangle that goes around this guy that does not contain the origin. This time I can go up and down as far as I want, but left and right, there's a restriction. So this time we still have a unique solution, but this time we can only say that it's going to be guaranteed on the interval 0 to infinity. Because once we hit 0, weird things can happen. And we're not necessarily guaranteed uniqueness anymore. So again, it all comes down to that initial value. It's not enough just to have the differential equation. You have to have an initial value to make any kind of sense of what kind of solution you have, whether it's guaranteed or not.
All right, so those are the existence and uniqueness theorems. That's how we tell if we know we're guaranteed a solution or not. And so that's something we might want to pay attention to as we go along. When we're given some new differential equations, maybe just do a real quick look at that and go, do we even bother trying to find it? Because if we're not guaranteed a solution, maybe we don't want to, right? Maybe we don't want to go through that effort. Or if we know we're guaranteed, okay, cool, let's go find it because we know it's going to happen. So it's a really easy check, really. It's just a matter of looking at what the y prime equals and looking for issues with continuity, either of the function itself or the partial with respect to y. All right, so questions on either of those? No, feeling all right? Okay, well then what I want to do with the rest of our time today is I want to show you some equations that can actually be transformed into separable, even though they're not. I'm going to show you two classes, two groups of equations that are kind of historical, and show you the techniques to convert both of them, both of these types, into separable so that we can make use of the techniques that we've already learned. Right, because separable is huge. If we can get all the variables separated, all you have to do is integrate both sides and you're done. So the first set I'm going to show you are what we call Bernoulli equations, and it is named after the same family. Remember that the Bernoullis, there were a bunch of them. Like from physics, you know, the Bernoulli equation that has to do with fluids flowing and all that. That was one of the brothers. There was another brother who was really into probabilities. So if you've taken stats and you remember Bernoulli from like the Bernoulli distribution and stuff like that, different Bernoulli, same family. So Bernoulli equations, I'm not actually sure which one of them is named after, because there was also the dad, by the way, who was also into the math and science. So one of them, but let's look at what we call Bernoulli equations.
So Bernoulli equations all take the same form. What they look like is this. So they get the form y prime plus p of xy is equal to f of x times y to the r. So if you have a differential equation that you can write like this, this is what we call a Bernoulli equation. So first things first, in terms of that r, if r equals 0, or if r equals 1, this is a boring linear first order. Right? Because if r is equal to 0, the y to the 0 just becomes 1, and that's exactly the form, the non-homogeneous form for linear first order. If r is equal to 1, we have f of x times y. Well, you can move that over to the other side, factor out the y, and now it's a homogeneous linear first order. So we're not going to bother with the r equals 0 or r equals 1, because those are boring, right? They just work. All right, so the question is, how are we going to go about solving these? Well, we're going to do the exact same thing we did last time. You may remember that when we were solving those linear first order, when it was the non-homogeneous, we just went with well, if we find a solution to the homogeneous, let's multiply it by something. But we're going to do the same thing here. We're going to let y1, this is going to be a solution to the homogeneous. Because we know we can solve those. That's the whole get negative p, integrate it, take e to that power, boom, there's our solution. Okay, so we're going to let y1 be a solution. Let's see if we can figure out what we can multiply to this y1 so that it's still going to be a solution. So you remember doing that before? That's what we're going to try again.
So let's see if we can figure out what u is going to have to be, what kind of form it has to take on so that this actually works. So what we're going to do is just plug it back in and see what spills out.
So if we let y equal u times y1, we need a y prime. So y prime is going to be u prime times y1 plus u times y1 prime, right? U is some function, so we need to make sure we keep that in there. And then let's put this in to the differential equation. So we're going to have u1 times y1, sorry, u prime times y1, plus u times y1 prime. We're going to add to that p times u times y1. And we want that to equal f of x times u times y1 to the r. So I'm just going back to this original form, and I'm substituting in for y. I'm putting in the u times y1. So now the algebra magic happens. I'm going to start separating this stuff up a little bit. We're going to get u prime times y1 plus u times y1 prime plus p of x times y1. And that's going to equal f of x times u to the r times y1 to the r. So do you see what the next step's going to be? I'm just curious if you've spotted this pattern yet. Because this even showed up on the homeworks, right? Where you said, where you went with, well, let's look at y2 minus y1 or whatever else. And we always related it back to the original differential equation. And you can see that here in the brackets. I've got y1 prime plus p of x times y1. That's exactly the form of the differential equation. And now we're going to look at what we know about y1. Y1 was a solution to the homogeneous, which means this right here is actually equal to 0. So that stuff in the brackets is equal to 0, which means it goes away. Well, if that goes away, what we're left with then, in terms of this equation, is u prime times y1 equals f of x times u to the r times y1 to the r. And this guy's separable, because we're going to be able to write u prime over u to the r is equal to f of x times y1 to the r minus 1. So even though Bernoulli, as it was written, was not separable, it turns into a separable differential equation. This allows us to solve for u. And then once we have u, we multiply that by the y1, and that's the solution to our original differential equation. So this is another place where the integrating factor showed up, where we go, all right, I know that the solution to the homogeneous isn't going to work, but let's multiply it by some unknown function and see if we can find it. All right, so this is kind of what you want to box. This is what you want to remember with these guys, because this is how we're going to find our u. we're going to let R be whatever power we had on Y at the start. And then this Y1, that's going to be a solution to the homogeneous. So let's try this out. Let's take an example and see how this goes. So I'll just leave that here for a second. But let's try this one. Let's say we've got x squared y prime plus 2xy minus y cubed equals 0. So this guy is not separable, but it is a Bernoulli equation. Let's rewrite it. Let's divide by x squared, and at the same time, move this bit with the y cubed to the other side. So we're going to get y prime plus 2 over xy equals y cubed over x squared. So let's pull the pieces out of this to sort of translate it into the Bernoulli. So p of x, that's 2 over x. That's what's multiplying y. It's the same p as before. G of x is going to be 1 over x squared, because that's what bit over here is being multiplied to a power of y. And then the other piece of information we need is r, and in this case, r is 3, because it's y cubed. So there's all the information. And now we're ready to jump into Bernoulli. So we need to start by finding y1, and y1 we find the usual way. That's the suppose this equals 0. So using this p, we're going to get y1 is equal to e to the negative integral of p. All right, so that's going to be e to the negative 2 natural logs of x, which is x to the minus 2 or 1 over x squared. Either way you want to look. Now I know we could have put a plus c in there, but remember y1 is any solution to the homogeneous. So I'm going to pick the easiest one, which is with the c equals 0. So there is a solution to the homogeneous differential equation. If we cover up this y cubed x squared, the 1 over x squared is going to make this thing equal 0. All right, so we found y1. Now we need to build our formula for finding u. So let me just remind you what it looked like. It was u prime over u to the r. That's equal to f of x times y1 to the r minus 1. So that's what we had found last time, or that's what we had boxed just a minute ago. So now let's put in our pieces for this specific differential equation. So we're going to get u prime over u cubed, because r is 3. This is equal to f of x, that was 1 over x squared, times y1, so x minus 2, to the r minus 1. So all I'm doing is I'm just putting that into all those pieces into their respective spots for what we just found for Bernoulli. So this is going to be u prime over u cubed equals x to the minus 6, or 1 over x to the 6, however you want to write it. All right, so how are we doing so far? Not too bad. I mean, we're slugging our way through this monkey math, but it's monkey math. Let's follow the process. All right, so now let's integrate. Let's integrate both sides. So we've got u to the minus 4 du equals x to the minus 6 dx. Integrate both of those, we get minus 1/3. Oh, whoops. Is u to the minus 3. We get minus 1/2 u to the minus 2. And that's going to equal minus 1/5 x to the minus 5 plus c. And it's at this point we have to put in that plus c, because that's what allows for the lots of different options. All right, so now that's an implicit form, but let's get it as an explicit form. So I'm going to multiply by minus 1. So I get 1 over 2u squared equals 1 over 5 x to the 5th plus c. This is a new c. It's now the negative of the other c. Let me get a common denominator here. So we get 1 over 2u squared equals 1 plus cx to the 5th over 5x to the 5th. And again, this is a new c. It was that old c times 5. So let's multiply by 2. So we get 1 over u squared is equal to 2 plus cx to the 5th over 5x to the 5th. And again, new c, that was this c times 2. So then I just flip over and I take a square root. So u is going to be the square root of 5x to the 5th over 2 plus cx to the 5th. And whether it's the plus or minus, kind of like we talked about last time, that will depend upon our initial value. Yay. Except we're not done. You kidding me? What else do we still have to do? Because what was this u? What was the whole point of this u?
As like a substitute, basically.
It was a substitute, but it's what we multiply to the y1. So we still have to take this and multiply it to the y1. Well, y1 was 1 over x squared. So what we're going to get, remember, y is equal to u times y1. So that's going to be the square root of 5x to the 5th over 2 plus cx to the 5th. And we need to multiply that by 1 over x squared. I am going to simplify this just a little bit, because that x to the 5th, I can pull out an x squared that cancels with that x squared. So we get the square root of 5x over 2 plus cx to the 5th. And that, my friends, is the solution to this differential equation. All right, so was that fun or what?
That was awesome.
In fact, you probably wish you could do that all day long. I'll give you like 20 of them, no problem. We'll have a grand old time. No, it's just like anything else. It's a process, it's a procedure. There are lots of steps, right? There are an absolute ton of steps. but it's the same thing every time. And what's going to make this complicated is really just the structure of the solutions, right? When you go and you solve that homogeneous, if that's something easy, okay, if it's something complicated, well, it's going to make that next step complicated because of the form that it takes on, right? So, and also the bigger the power that we have, the bigger the R, the gnarlier this gets in terms of the kind of root that we have to take. But there you go. So there's a group of equations. They're called Bernoulli equations. And like I said, they are always separable if you do this little trick. All right. So I think I'm actually going to stop here. I know we've got a little bit of time left, but I think we're going to stop just because this is kind of mind numbing. I don't really want to show you another example because it's just the same old, same old. So let me just go ahead and stop the video.